So we're told here that f of x is equal to this infinite series, and we need to figure out what is the third derivative of f evaluated at x equals 0. And like always, pause this video and see if you can work it out on your own before we do it together. All right, so there's two ways to approach this. One is we could just take the derivative of this expression while it's in sigma notation. The other way we do it is we could just expand out f of x and take the derivative 3 times and see if we get an answer that, I guess, makes sense. So let me do it the second way first. So let me just expand it out. F of x is equal to, let's see, when n is equal to 0, this is negative 1 to the 0, which is just 1, times x to the 0 plus 3. So it's going to be x to the third over 2 times 0, so that's 0 plus 1 factorial. So that's just going to be over 1. Then the next term, when n is equal to 1, well, now it's going to be negative 1 to the 1. So now it's going to have a negative out front. Negative, and there's going to be 2 times 1 plus 3. So that's going to be x to the fifth power over 2 times 1 plus 1. So it's going to be 2 plus 1 is 3 factorial. So it's going to be x to the fifth over 6. And then when x is equal to 2, this is going to be positive again. It's going to be x to the 7th power, over 5 factorial. Is that right? Yeah, 5 factorial. And 5 factorial, actually, let me just write that out as 5 factorial. 5 factorial would be, what? It would be 120. It'd be 5 times 4 times 6. So it'd be 120. But we could just keep going, minus, plus, and it goes on and on and on forever. Well, now let's just take the derivatives. So f prime of x is going to be equal to, we're just applying the power rule here, it's going to be 3x squared minus 5/6 to the 4th plus 7 over 5 factorial x to the 6th. I'm just applying the power rule. Minus, plus, we just keep going on and on and on forever. The second derivative, f prime prime of x, is going to be equal to, apply the power rule again. It's going to be 6x to the first minus 4 times 5 over 6. I'll just write that as 20 over 6, x to the third, plus 6 times 7, so it's 42 over 5 factorial, x to the fifth, and we're just going to keep on going, minus, plus, keep going, or alternate between minus something, then plus something, on and on and on forever. And then we get to the third derivative. The third derivative is equal to, let's see, the derivative of 6x is 6, and then we have minus 20 times 3 is 60 over 6, which of course is 10, x squared, plus 5 times 42 is what? 210 over 5 factorial times x to the 4th power minus plus over and over and over again. And then we just evaluate this at 0. F prime 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 at 0. Well, when x is equal to 0, all of these terms with x's are going to go to 0, and you're just going to be left with this 6 here. So f prime prime at the third derivative evaluated at 0 is just equal to 6. Now, another way that we could have tackled this is just kept it in this sigma notation. So we could have said that f prime of x is equal to the infinite sum. And actually, let me line them up. So this is where we did f prime of x expanded out, but we could have said f prime of x is equal to the sum from n equals 0 to infinity. And you take the derivative here, you're going to get, and you're taking the derivative with respect to x. So for that purpose, you assume everything else is, well, the n is just going to tell us which term is going to tell us how we change from term to term. So if we take the derivative with respect to x here, use the power rule, bring the 2n plus 3 out front. So it's going to be negative 1 to the n times 2n plus 3 times x to the decrement, the exponent, 2n plus 2 over 2n plus 1 factorial. And then if you want to take the second derivative, and this is the same thing as this. If you take the second derivative, f prime prime of x, well, now we're taking the sum from 0 to infinity of negative 1 to the n. Let me move over to the right a little bit so we have some space. And now we take this exponent out front. So you're going to have 2n plus 3 times 2n plus 2. All of that's going to be over 2n plus 1 factorial. and this is going to be times x to the 2n plus 1. All I'm doing every time, it seems really complicated, I'm just taking the exponent out front, multiplying it out front, and then decrementing it. So 2n plus 2 minus 1 is 2n plus 1. And then if I want to take the third derivative is the sum, n equals 0 to infinity, negative 1 to the n. We take this, bring it, multiply it. So we're going to have 2n plus 3 times 2n plus 2 times 2n plus 1. All of that over 2n plus 1 factorial. And then that is going to be times x to the 2n power. Now let's evaluate this thing when x is equal to 0. So f prime 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 of 0 is going to be the sum from n equals 0 to infinity of negative 1 to the nth power. Now this is going to be interesting. We're going to have all this business, 2n plus 3 times 2n plus 2 times 2n plus 1, all of that over 2n plus 1 factorial times 0 to the 2n power. Now you might be tempted to say, well, hey, if 0 to these different powers, maybe everything's going to be 0. But remember, we're starting at n equals 0. So for any n that's not equal to 0, this 0 to that power is just going to be 0, and that term's going to disappear, kind of like what we saw when we expanded it out. And so the only term that matters here is when n is equal to 0. And so this is just going to be equal to, because for n equals 1, 2, 3, 4, 5, all the way to infinity, this thing is going to dominate. It's just going to multiply. It's going to be 0, and you're just going to zero everything out. And so this is just going to reduce to the first term when n equals 0. And when n equals 0, it's going to be negative 1 to the 0. This is going to be, which is just 1. So let me just write that as 1 times, this is 3 times 2 times 1 over 1 factorial, and then times 0 to the 0, which is equal to 1. So this is equal to 1, and so this is equal to 6. So either way, I think the first way we did it was a little bit more straightforward, a little bit more intuitive, closer to what you might have seen before. But it's important to realize that we did the same thing both times. We just kept it in the sigma notation on this time to the right. And this technique is useful because you'll see it a lot in math, where you might want to do things in a little bit more of a general way. And so it might be helpful to take the derivatives while you stay in that sigma notation.